All good things must come to the end. And just like that, this is going to be our last lecture, unfortunately. It's very sad, and we wish we can just keep on going and going and going, but it's going to be our last lecture. We do have to stop at some point. But it's going to be a very nice lecture. This is a very important theorem in topology and in manifolds, and we have the tools to prove it. And it's called Poincare duality. Now, before we say what Poincare duality is, maybe it's interesting to ask the question, if we want to continue, so how to continue? So let's say you're interested in topology, you're interested in what we're doing. What are the different ways you can continue with this topic? So these are just some of the different ways. You could do something called knot theory. It happens to be its own special field within topology. Another topic you can move into, you can learn about what we currently know about three-dimensional manifolds. Two-dimensional manifolds are classified, but three-dimensional manifolds, that is an open problem. Poincaré conjecture was a problem in three-dimensional manifolds. These are a little bit related to each other, but here you're not really interested in knots. You're interested in, let's say, compact three-dimensional manifolds and what can be said about them. There's a lot of material that is done on that, and people are working on that. Another topic you can continue in is you can relearn homology and cohomology, and this time more abstractly. We did not say everything there is to be said about homology, obviously. We did say that there is something called homology with arbitrary coefficients. They do not necessarily have to be integer coefficients. We can talk about cohomology done in a more abstract way as well for any topological space. In fact, there is something called a cohomology ring. So once you have cohomology, you can give it the structure of a ring, so you have more algebraic structure to use. So it's not just a vector space, it becomes an algebra. So one can talk about that. Then you can also learn about the more abstract ways of characterizing homology. So that's like another path that one can go into. One can, of course, as was mentioned, one perhaps might be interested in combinatorial, and I'm going to pair this with computational topology. So here you might be interested in simplicial complexes and high dimensions and how to compute that, and the different kinds of applications that go along with it. There are some applications of that stuff in what they call nowadays topological data analysis. So that could be another direction one can go into. Another direction you can move into is, if you like differential forms, you can do differential geometry, where it's no longer a smooth manifold, but it's a smooth manifold with what is known as a Riemannian metric. It's not actually a metric in the usual sense. It's not about a distance between 2 points, but it is a type of metric that allows you to do geometry. And then you introduce geometry on the manifold, and you can talk about that. Another direction one can move into is what we mentioned is a field of differential topology. So what differential topology is interested in, you have a manifold, and on that manifold, you have the exact same manifold, and on that same exact manifold, you can put different kind of smooth you can put different kinds of smooth atlases on that manifold, and you can ask, are they diffeomorphic? Are they genuinely different from each other, even though the topology remains the same? So these are just some, and you can probably make this list twice as long. So there's certainly a very long path ahead on the different ways such a course can potentially be continued. But we're going to talk about Poincare duality. So let's return back to that. Now, I should just give a disclaimer that this lecture is going to be challenging. This is going to be a challenging lecture, but it will be complete. We will mention all of the ideas that are necessary to prove Poincare duality, and we'll state it properly. However, there's going to be some missing details, for the simple reason because we do not want these lectures to turn into a very long lecture, even though we've had this theme that everything we do always goes on for much longer than it is. But the details will be the kind of details you can either fill in yourself or maybe look it up. But the lecture will be complete. Like, we'll show all of the ideas that go into Poincare duality. So let's start with what the theorem actually says. So maybe I should mention a fact. So let's write a proposition over here. And if you want to see the proof of this, this is going to be in the Bot and 2 book that I keep on referencing in the last few lectures. So the proposition here is that if X is compact, so this is a compact manifold, we're working with manifolds, so if X is compact, then its homology of every dimension is finite dimensional. I do not feel like proving this because it's going to make the lecture a little bit too long. It is an interesting proof. Well, I should say it is believable, because anytime you see the word compact, it often is paired with the word finite. This is our experience with compactness. So it is fairly believable. But what's the idea? The idea is basically that if you have your manifold, so let's just draw it something like this. So you have your compact manifold, and you're going to cover it by open sets that are homeomorphic to Euclidean spaces that are contractible, so they have trivial homology, and so on. And because this space is compact, you can find a finite cover, and it's going to be a proof by induction on how many open sets you have in that cover. And it's also interesting in the sense that the way it's proven in Bot and 2 is they equip the manifold with a geometry. And the reason for this is you want these open sets, as we mentioned before, to be geodesically convex. And the reason for this is that when they intersect, then they intersect on something that's geodesically convex. And so under the charts, so when you have your chart mapping Euclidean space to that open set, on the overlap, you're going to have something convex over here. And so on the overlaps, the homology on the overlaps will be trivial because this is convex, so it shrinks down to a point. And that's the idea. And it's a proof by induction where it's the number of such open sets that you're using. It takes a little bit of work to figure this out. It's not immediate, but it is an interesting proof. And we're just going to accept it. So you can look at that reference. If the space is not compact, by the way, then the homology groups do not have to be finite dimensional. Just to give you a very simple example, just take the real plane and introduce a sequence of punctures like this. Just introduce a sequence of punctures, and then you will have an infinite dimensional vector space, so like an infinite number of holes. So it does not have to be, as you can see, a finite dimensional space. But if it is compact, then it will be. So what we're going to do is, so let's introduce some notation. Let's use lowercase hi of x to just denote the dimension of this vector space. It's a finite number. So that's going to be the dimension of this vector space. And these numbers, they have a name. They're called the Betti numbers. So the Betti numbers, basically, one way to interpret them, you can interpret these Betti numbers as counting holes of various dimensions. So for instance, if you have the sphere, then the zero-dimensional Betti number is 1, because the zero-dimensional homology is a one-dimensional space. The one-dimensional homology of the sphere is trivial, so the first Betti number, so the 0th Betti number is 1, the first Betti number is 0, and the second, I'm writing my subscripts in the incorrect position. The second Betti number would be equal to 1, right? The second homology of the sphere is isomorphic to R. That's a one-dimensional space. And then all of the larger dimensional ones are going to be 0. This is for I bigger than 2. So these are the Betti numbers. So you get this sequence of numbers, 1, 0, 1, and then the rest of them are 0. Okay, so that's what we have for the sphere. If you do this for the torus, if it was the torus, then it would be 1, 2, 1, right? That would be for the torus. The first dimensional Betti number would be 2 because the first homology of the torus is R squared. So this is how we define the Betti numbers. And they're going to be finite numbers because if it's a compact space, we're going to restrict our attention to compact spaces, then based on this proposition, they're going to be finite numbers. And let's state Poincaré duality. This is theorem, and it's a very nice theorem. This is a very nice way to conclude our semester. It's going to use many of the ideas that we talked about in a very nice unifying way. This is what we call Poincare duality. And it says that if X is a compact manifold, and we have to assume that it is an oriented manifold. So we're going to assume that we are familiar what it means to be oriented. We did talk about that before, what it means to be an orientable manifold, but we're not going to go through the definition again. We had a very long lecture on that. But using the definition from before, if we have an oriented manifold, then if we were to, let's also assume that this is an n-dimensional manifold. So then if we were to calculate the ith Betti number of this manifold, that would be the same thing as the n minus I Betti number of X. So here I, which we should say for I, of course, between 0 and n, right? Between 0 and n. Because otherwise, this is not going to make sense. If I exceeds n, then this is negative dimension. I mean, I guess you will just interpret a negative Betti number to be 0, because in that case, this homology is 0. So, I mean, I guess if you want to remove this restriction, you can by just interpreting that to be 0. So it's not that big of a deal. I mean, it's up to you if you want to include that in there. But so that's the statement. It's a pretty amazing statement. I mean, think about what you're saying. You're saying that, so we often talk about, this is a terminology that maybe you've seen before. If V, so let's suppose V and W are vector spaces, and V is contained in W, then we talk about this thing called the codimension of V as a subspace of W. And the codimension is, it's the dimension of W, so assuming they're finite dimensional, minus the dimension of V. So the codimension is like the missing dimension that you need to reach W. That's what you call the codimension. And the dimension of our manifold is n. So what the Poincare duality theorem is basically saying, that if you count how many holes you have of dimension I, you will get the same number if you looked at the codimension of that holes, of the number of holes. So pretty amazing result that it works out this way. And this is what we call Poincare duality. So there's some immediate consequences from this. We can mention some corollaries. And of course, what we want to do is we want to prove this theorem. That's what we want to do. We want to prove this. Now, I want to make a remark here, somewhat nice to know. It is possible to prove this topologically. And if you're interested, you can see, for instance, Alan Hatcher. He proves this in a topological way. What I mean is without using differential forms. we are going to use differential forms. We will use smooth manifolds. We will use differential forms. We will use integration. We're going to bring out all of that very nice machinery that we've developed, and you get to see how it gets used again for something else. But it is possible to prove this topologically. However, it is harder. But it is harder. It happens to be more general, but it is harder. When I was a graduate student, I had a professor of topology who proved this result following Hatcher. And the only thing I remember from that class is it took him multiple classes to work up to the proof. And in the end, I don't think anyone understood what he was saying. So it was not a very good way of spending class material when that time could have been spent better on something else. But because we're using differential forms, our proof is going to be a lot nicer. And in fact, as we've said, that's the beautiful theme of the Bot and 2 book, where you redo topology, but by using the machinery of differential forms. So it's going to make the proof of this a lot simpler. And now let's mention some nice corollaries here. So here is a corollary. Corollary 1, which, if you think about this, this is by no means obvious. If X is compact and orientable, so orientable means there is a way to orient it consistently, then the top dimensional Betti number, so, well, so n over here refers to the dimension of our manifold. This is the top dimensional, because the moment you go beyond that dimension, they're all going to be 0. So this is the top one you can reach. So the top dimensional Betti number would be equal to 1. I guess I have to be a little bit careful over here. We have to assume that it is connected or path connected. We do have to assume it is connected, because clearly it's not true. Just take 2 disjoint copies of 2 spheres, and then this is a 2 chain, and this is you have 2 distinct 2 chains. So yeah, you have to assume it's connected. But with this very mild assumption, this is what you have. And how do you prove this? Well, it's actually very simple. You just use Poincare duality. H0 of x, Hn of x would be H0 of x. But H0 of x, because it is connected, there's just one component that's equal to 1. So it means the top dimensional cohomology is one-dimensional space. So corollary 2. This is quite nice. The projective plane is not orientable. Now, we already know this. We proved that before. Let me quickly remind you how we proved this. Our proof was quite complicated. What we did first is we proved very carefully. It was a very long proof, but we did prove that the Mobius band was not orientable. The idea was that P2 contains the Mobius band. I think I put the dots on the wrong letter, but that's okay. P2 contains the Mobius band. And so if P2 was orientable, the Mobius band would be orientable, and we proved it's a nice proof, but it's quite complicated, that the Mobius band is not orientable. But now you have an immediate proof by using Poincare duality. Because so P2, this is a 2-dimensional compact manifold. It's also connected. So if it was the case that it was orientable, then it would mean that the top the top Betti number should be equal to 1. But is that true? We know that the two-dimensional the second homology group of the projective plane is trivial. Actually, the first homology group of the projective plane is Z mod 2, but this one is trivial. And so it will then follow that, So here we use the Rham theorem. So it would mean that the two-dimensional homology of this space would be isomorphic to the dual. So this is the Rham theorem. And by the way, the Rham theorem, in contrast to Poincare duality, does not require us to assume that the space is orientable. So from here it follows, of course, that this homology group, its dual, would be trivial. So the second homology group of the projective plane is therefore trivial. So now, yeah, so it's a nice way to prove this that is fairly quick by using this very nice theorem. The third corollary that I wanted to show you, it's also quite nice. Corollary 3. So if X is compact and oriented, and the dimension of X, so the dimension of the manifold is odd, is an odd number, then the Euler characteristic of the manifold is 0. That's a nice, surprising result. It has to be odd. Okay, so how do you prove this? Well, I'll give you a proof of corollary 3. Here's the proof. So we triangulate. Well, actually, yeah, I mean, you triangulate X, and then you let n subscript I denote the number of I-dimensional simplices of the triangulation. Then the Euler characteristic is computed by this alternating sum. So let's say the dimension of the manifold, we call it capital N. So it goes up to capital N. And it will be this alternating sum of these numbers. And we've proved that the Euler characteristic is a topological invariant. It does not matter how you triangulate. So you pick a triangulation and then you use it to compute the Euler characteristic. But then we saw, and this was done before. So this was proved before. So if you forgot, you can always go back to that lecture that we have on the Euler characteristic, and then you see that this alternating sum can also be expressed using it's an alternating sum of the ranks. So you're going to compute the rank of the homology groups. And then we saw that the rank of the homology groups, that's the number of z factors, these are finitely generated groups, that would actually be equal to the dimension when you dualize this into a vector space. So that would be equal to the alternating sum. This will be the dimension of when you dualize this into a vector space. But the dimension, when you dualize this, now we use the Rham theorem. So look at that. This is so nice. We're using every idea that we've talked about. And now we use the Rham theorem. This is the Rham theorem. This is the sum, the alternating sum of the dimension of the homology groups. The dimension of the homology groups. Okay? And this is what we call the Betti numbers by definition, from 0 to capital N minus 1 to the I. So this is going to be hi of x. So it's the alternating sum of the Betti numbers, but now you use Poincare duality that, you see, you have this duality that I and n minus 1 and n minus I, they're the same dimension. So you have cancellation. And this is equal to 0 by Poincare duality, and the fact that we have what is known as a telescoping sum. Maybe to make it easier for you, make this an odd number, let's say 3. So it's very easy to see what would happen if you write this out. So you would have, let's just write h0 without x. h0 minus h1 plus h2 minus h3. And then there's no reason to go any further because the rest of them are 0. And then these cancel. That's Poincare duality. There's a duality between 0 and 3, and there's a duality between 1 and 2 because they add up to the dimension 3. So then these cancel, and in the end, you're left with 0. So this is another extremely nice consequences of Poincare duality. So these are just some of the corollaries. One can imagine more corollaries following from this. And now what we have to do is, so that's the statement of the theorem. And if you're perfectly happy with this result and you're not interested in anything else, then this is fine. But maybe you want to understand how to prove it. And I think understanding the proof is actually more interesting. So the rest of the lecture is going to be dedicated to proving this result. And as we said, the proof is challenging. It might be even very long. I have no idea how long it's going to be, but it will be complete. We will present all of the ideas that we need in order to make this work out. So let's take this away and start discussing the proof of this amazing theorem. Now we're going to discuss the idea of the proof. This is the idea of proof of Poincare duality. Well, actually, before I get into this, there is something that I forgot to say. This is just going back to potential continuation. If there was a Topology 3 course, what can you learn? So I did forget to say you can learn about homotopy theory. And this is where you talk about pi n. So instead of talking about the fundamental group, you can talk about higher homotopy groups. And that itself is its own thing. As we've said, these groups are exceptionally difficult to compute. But that's like another thing you can go into. But anyway, let's return back to how you prove Poincare duality. Now, the idea here is actually, it's very similar to the proof of the Rham theorem. So let's recall what the theorem says. We said that if X is compact, is a compact manifold, it actually does not need to be a compact manifold. But if X is compact, notice here we do not assume that it's orientable. So compactness here is just convenient because we can cover X using finitely many open sets with a certain property. But you do not need that. It could be a little bit more general than this. But if X is compact, I'm just writing it the compact way because that's the way we formulated it. If X is compact, then if you were to look at the ith cohomology of X, that is isomorphic to the dual of the ith homology of X. I guess we can maybe write it like this. And of course, this is just by definition, these are the homomorphisms from the homology group into the reals. If you consider all homomorphisms, they form a vector space. Obviously, it would be silly to say that this is isomorphic to this, because these are two different kinds of objects. This is a group, this is a vector space, but by taking Rham, you've turned this into a vector space, and this is an isomorphism of vector spaces. And in fact, not only are these isomorphic, but we can say what the isomorphism is. So these are isomorphic, and we have something that is known as a natural isomorphism. So they're not just isomorphic, but they're isomorphic in a natural way. And this is going to be very important. What do we mean by natural? What we mean by natural is basically it's a type of isomorphism that preserves commutative diagrams. So let me show you what I mean. So let's say you have, well, before I tell you what it means to be natural, I guess I should just remind you what the isomorphism is. So you pick something in the Cohomology class. Okay, this is in the Cohomology class. And you have to assign it to something in the dual. So that means it has to be something in this, in Rham. So it has to be a homomorphism from the homology group to the reals. So what kind of homomorphism does it give you? So to describe what the homomorphism is, I have to tell you how a homology class is mapped. So now you pick something in the homology class. So you pick a cycle, and then you map that cycle to a real number by integration. So you integrate omega over the cycle. So this is the isomorphism, and this happens to be a natural isomorphism. Now, what do we mean by natural over here? So what we mean by natural is as follows. So suppose, so say, what do we mean by natural? So let's say that x and y are compact manifolds, and f from x to y is a smooth map. Then this function, it induces a mapping on cohomology. So we have two induced maps. We have an induced map on homology, which is basically you take a class and then you map it by composition. You basically say F composed C, like this. This does not exactly make a lot of sense, but you can figure out what this means, because a cycle is a formal sum of simplices, and simplices are maps. So then you just compose it with the map, and then you create like a formal sum out of that. But we talked about this as the induced map on homology. But then there's a induced map on cohomology, but this one goes in the other direction. This is from hi of y to hi of x. This is the one that's given by pullback. So if you give me a form, so you give me something in the cohomology class, but in particular this is a form defined on y, then you can pull it back. So pulling it back basically is substitution. Basically, I mean, this is massive abuse of notation, but that's essentially what we're trying to say. It's just the composition goes the other way. So remember what I said. Some of the things that we're going to be doing in this lecture, details omitted. You can figure out how to explicitly do that. I do not want to go there because that will just make this lecture be unnecessarily long. Okay, so we have, this is an induced map on abelian groups, and this is an induced map on vector spaces. So now look at this. If we take the dual of this, remember, dualizing, taking Rham, right, the Rham functor, it's a functor. So if we dualize this, this might look a little bit funny. We're going to have the dual of f, so it's like 2 stars. This is going to take us from the dual of this homology to the dual of that homology. Okay, so now we can create a diagram out of this. So we have a map of vector spaces going like this, given by F star. Then we have a map of vector spaces on these vector spaces, given by the dual of the induced map on homology. And then we have the isomorphism coming from de Rham's theorem. Okay, this is the isomorphism that's coming from the de Rham theorem. And when we say that this is a natural isomorphism, it means that such a diagram will commute. But why is this important? Why do we care that this isomorphism is natural? So here's the reason why we care. Let's go back to the idea behind the proof to see how it works. The natural isomorphism is part of the key idea of the proof of de Rham's theorem. So here's how it goes. So this is a very quick outline. We talked about this in the previous lecture, but a very brief outline. So briefly, if X is compact, we can cover X by open sets. X, let's call them U1, UN, where each UK is homeomorphic to RD, where D is the dimension of X. So each UK is isomorphic to RD. Okay, and the U's, so the U1 to the UN, they intersect. Either they intersect in an empty way, they intersect. So maybe I'll write it like this. If you take UI and you intersect it with UJ, maybe I should not call it I'm going to be using I for cohomology. So maybe UK, UL. And if you intersect them, that this is either empty or it's something that is homeomorphic to an open convex subset. Convex subset of RD. Okay, so basically what we're saying is here's your manifold, here's UK, here's UL, and if they intersect, it does not matter what chart you pick, but let's say it's RD, and the place where they intersect, that's going to be a convex subset of RD that is getting mapped to that intersection. You can use the blue chart. It's also going to be convex. Does not matter which one you use. And furthermore, this property continues. I'm not going to write it out over here, but this property continues to hold on when you intersect further. So if you were to take 3 of them and intersect, it will be empty, or otherwise they will still intersect in an open convex subset of RD. So that's what you do. You cover X by open sets that are all homeomorphic to RD, and they have this property. So what's the reason for this? So the reason for this, so the idea here, the idea is that we prove the de Rham theorem locally, so on these small open sets, and then use the Mayer-Vietoris sequence to glue all that data together and prove the de Rham theorem globally. So that's what we're doing. Okay, so in a way, it's a proof by induction, It's a proof on induction on the number of open sets that you have. So let's say that you have two open sets, to keep it simple. So say X is a union of two open sets. And once you see how it works for two, you can then easily generalize that further. But so let's say X is a union of two open sets, and the open sets, they're both homeomorphic to RD, and when they intersect in something of this type. So then when you use the Mayer-Vietoris sequence, you actually have two Mayer-Vietoris sequences. You have one of them for cohomology. So this is the one for cohomology. So the one for cohomology will go like this. You will go HI of X, right? That's the union. Then that goes to HI of U. This is the restriction map on differential forms. Then it goes to HI U intersect V, like that. And then you have one that precedes it. So here we're going to assume that I is at least 1. Otherwise, there's not much to prove. This is U intersect V. And this is HI minus 1U plus HI minus 1 V, like this. So this is the Mayer-Vietoris sequence for cohomology. But then you have the Mayer-Vietoris sequence for homology. This is the one that's going to go like this, HI. I'm going to leave a gap over here because I'm going to dualize it. But you have HI of X, then it will go to HI minus 1 U intersect V. So I wrote U1 and U2, so maybe for simplicity, let's just call it U and V. And then the one that goes after that would be HI minus 1U plus HI minus 1V. And then you have one over here. This is HI of U plus HI of V. And then you have one over here, HI of U intersect V. So this is an exact sequence of vector spaces. And this is an exact sequence of abelian groups. Notice they do not exactly match. They're kind of going out of order, right? The one in the middle, they coincide, but this one, it's sort of going there. But if you dualize it, you change the arrows. So you're going to apply the dualizing functor, and you will end up getting HI dual of X. Then you will have HI dual of U plus HI dual of V. And there's a missing detail over here. But basically, when you dualize a direct sum, that is isomorphic to dualizing each of the two pieces. So that's why you can kind of split it like this. I don't want to bother to go there. That's not the important part here. And then you have this one. Then you have HI star, U intersect V. Then you have one going like this, HI minus 1. Of that intersection, and then we have HI minus 1 dual of U plus HI minus 1 dual of V. We can forget about the one on the bottom. We do not need that anymore. And now, recall what we said. We have a de Rham map between all of these. So from this one to this one, we have a de Rham map. Okay, we have a de Rham map on all of these. So the de Rham map is given by integration. I know that we've defined the de Rham map with the assumption that the manifold is compact, but it really does not matter. You can do it for any manifold you have a de Rham map. So these are the de Rham maps. These are the ones that are given by integration. And the idea is, and this is where we use the thing, what we call the 5 lemma that we had on the homework, that if these two are isomorphisms and these two are isomorphisms, then the one in the middle is an isomorphism. Now here's the key idea. Since the de Rham map is natural, this diagram commutes. That's exactly what we mean that the de Rham map is natural. that we have a commutative diagram out of this, that the isomorphism in the Rham's theorem is not just an isomorphism, but it is a natural isomorphism. And this is important because the de Rham map, all of these are the de Rham maps, and you have a commutative diagram out of this. And so we want to prove that the middle one is an isomorphism. Why is this an isomorphism? Well, this is where we use what we call the Poincaré lemma. We talked about this previous lecture, but I think it's a good idea to remind you again what this says, because it illustrates the point of what we're doing. The Poincaré lemma says that if, let's say, C is an open set in RD and is convex, is an open convex subset of RD, then its homology would be trivial for I bigger than 0. Now, you could argue that if it's a convex set can always be homotoped down to a point. And so you have a homology of a single point, which is trivial. But you see, you're cheating a little bit. You're calculating the cohomology by using the homology. And that is, after all, what the de Rham theorem is about. So the whole point of the Poincaré lemma is sort of like a very special case of the de Rham theorem applied to very special subsets of Euclidean space. And you prove this not by using the de Rham theorem, because that would be circular reasoning, but the way you prove it is you show why every form of degree I, which has 0 derivative, comes from a derivative of a smaller degree form. That's what it means to have 0 cohomology. So the Poincaré lemma actually constructs explicitly basically what the antiderivative is, right? You're saying that a form is the derivative of something else, right? So maybe to write it out. So we want to show that if omega is a form of degree I on C, and its derivative is 0, because that's what it means to be in the cohomology, then there is a form of a previous degree with the property that allows you to express omega as the derivative of that previous form. That is what it means to be cohomologically trivial. So basically, you have an antiderivative. So Poincaré lemma, it constructs explicitly the antiderivative for you. And now look at this. The reason why this is an isomorphism is for trivial reasons, because U intersect V, that is homeomorphic to a convex open subset of RD. That's our assumption. So this is trivial. And now, but this is cohomology, this is homology. Homology, this is convex, so it homotopes to a point. So its homology is trivial, which means its dual will also be trivial. So this is 0. And the reason why this is an isomorphism has precisely to just do with the fact that you're just mapping 0. It's automatically going to be an isomorphism. So this is and all of these for the same reason. The Poincaré lemma is basically justifying why these are all going to be 0. Right there, and then the one from here to here, this is proving it in the special case because these are homeomorphic too. So this is going to be 0 and 0 and so on. So these are all zeros. So all of these, all of the outside maps are homeomorphisms, which means that this map will have to be I'm sorry, I said I meant to say isomorphisms. It will mean that this one has to be an isomorphism as well. Okay, and it's the it's the fact that it's a natural isomorphism that is important here. And you prove it for 2, and then you kind of, so I mean, this is kind of what we said. You would prove it for a union, U union V, and then if X is a union of 3 sets, then you use what you've just proven for 2 sets as your assumption, and you build into 3 sets. So it's sort of like a proof by induction. And then from there, everything follows. But that's the idea. So now let's discuss how we're going to prove Poincare duality, which is going to actually be very similar to this. So now we're going to discuss the idea of proof for Poincare duality is very similar. So I'm going to say this is the restated theorem. This is not the way we said the theorem originally, but this is going to be the restated version. So here's how it goes. If X is compact and oriented, now you might be confused and you might keep on wondering, why do you need it to be oriented? Well, we'll get back to that very soon. If X is compact and oriented, then we have a map, we have an isomorphism from the ith, let's say D is the dimension of X. Then we have, so we want to say that this is isomorphic to this, but that's not the way we're going to do it. Because we want to construct an isomorphism, and we also want this isomorphism to be natural, because we're going to use the same technique. We're going to prove Poincare duality locally on small open sets for which it is easy to verify for almost trivial reasons, and then we're going to glue all of that data together and conclude that it is true for the entire manifold. So it's going to look a bit bizarre, but instead of it is true, like it is true that these two are going to be isomorphic. They have the same dimension, so they have to be isomorphic. But we want a natural isomorphism. And the way that this is going to go is that we have a natural isomorphism, and it will not go to n minus 1 of x. It would rather go to the dual of n minus I of x. We have to use the dual here because that's the way we get a natural isomorphism. And this is going to be a natural isomorphism. So this is the dual of a vector space. By the way, so here's just, so note, if V is a finite dimensional vector space, it's a very easy exercise to show that V is isomorphic to its dual. But there is no natural isomorphism. The way you show this is simply by counting dimension. V is a finite dimensional vector space, so it has a basis, and then you can use that basis to create a dual basis, and then show that the dual basis is indeed a basis and they have the same dimension and all that stuff. But the problem is that the isomorphism depends on how you choose a basis. If you ask another person for the isomorphism, they'll pick a different basis, and so they'll have a different isomorphism in the end. So the isomorphism is not natural. So even though it is true that the dual of this homology group is isomorphic to the one without the dual, the problem is that you do not have a natural map from this one to that one, which is an isomorphism. It's going to be important to have a natural isomorphism in the exact same way. It's the same idea that goes into proving the Rham theorem. So this is the way it's going to go. And what is the isomorphism? So amazingly, it's almost the same isomorphism as in the Rham theorem. So here's how the isomorphism goes. So you're going to pick a cohomology class, omega, and where do you map it to? Well, it's in the dual of this. So what's the dual of this? The dual of this is simply Rham of h n minus 1 x to r. So it's a homomorphism, or a linear map from this vector space to that vector space. So you have to give me an n minus I form, and I have to tell you how you map it to a real number. So here's how it's going to go. You're going to give me an n minus I form. Let's call it eta. Eta is going to be an n minus 1 form in the cohomology. And I have to create a homomorphism out of this. So I have to tell you how to map forms into the real numbers. And I do this by integration again. But previously, you see, previously we mapped a chain into a real number. But this time we're mapping a form into a real number. And the way we do that is we integrate This time we integrate over the manifold itself. It's a different type of integration. Not integration over a chain. This is the other type of integration we talked about. It's the integration over the manifold itself. And what are we integrating? Well, X is a d-dimensional, well, I call it n over here, so I guess I should call this n. X is an n-dimensional manifold, so, and we can only integrate a top form. It has to be a form of degree n can only be integrated over an n-dimensional manifold. At the moment, omega is an I form, and eta is an n minus I form. But if you put them together, then you get an n form. So you just put them together with the wedge product. So you take omega, wedge, eta. Actually, it does not matter in what order you write this. You can write eta first and then write omega. It does not matter. So let's say you write omega first. This is now an n form. This is an I form. This is an n minus I form. And together, when you wedge them, you get an n form. So this is an n form. This is an n-dimensional manifold. And it's important that it's oriented because integration on manifolds, not on chains, requires that the manifold has to be oriented. Otherwise, this is not well defined. You see, with the Rham theorem, you're integrating chains. You're not integrating over the manifolds. When you're integrating chains, that's not a problem. You can even say the chain itself gives you the orientation, if you know what I mean by that. But if not, then you can just ignore what I just said. But when you're integrating chains, that's why it does not matter if it's oriented or not. But here, that's why it's going to be important. Otherwise, this is not going to make any kind of sense. So this is what you have. So now, this is where I mean missing details. I leave it up to you to try to figure out what I mean by this. But basically what it means is, if you go back to the definitions, omega is a coherent family of forms in the atlas that defines X, and eta is another coherent family of forms. And the way you take the wedge is you just take the coherent family of forms in every chart and you just wedge them in the Euclidean sense, right? By just juxtaposing the differentials together. And then one does indeed have to verify that's a coherent family and all of that stuff. But that's what I mean, missing details. So this is what we have here. Okay. So you also have to verify that this is a linear map. That's actually fairly easy because you're using integration. Integration is a linear operator. So that's going to be where we're going to proceed. But there's going to be a problem here, unfortunately. There's going to be a problem. I actually think it's a good idea for me to explain to you again what this means, because it's not something that we've really used before. I know we defined it once before, but it will probably be a good idea to explain how this is computed. But let's put that aside for now. What I wanted to say is we have a problem. And here's where the problem lies. And this is why the proof of Poincare duality is not as easy as the one for the Rham theorem. So here's where we're going to have a problem. You see, when you're integrating, it's important that the form is compact, because you're going to get something that is going to be a finite number and all of that. The integral will exist. But how would you prove Poincare duality by mimicking the proof of the Rham theorem? What you would do is you would take your manifold and you will start covering up by small open sets, right? By small open sets on which it is trivial to verify Poincare duality. But you're going to have a problem. And the problem is that when you restrict everything to these smaller open sets, you will basically be talking about, you're going to have integral over U, where U is one of those open sets that makes up this family, right? Just go back to the proof of the Rham theorem. How do we prove the Rham theorem? You cover X by a family of open sets for which it is trivial to verify the Rham theorem. And then you use the naturality of this map to build two exact sequences coming from Mayer-Vietoris. You have all those isomorphisms, and then you can glue things together on the union to conclude that this is an isomorphism. But you have to work with the individual open sets that make it up. And the problem is, what would happen if you were to replace X by one of those open sets? The problem would be this mapping, this natural mapping, will take omega and will map it to the integral over U. It's the integral It's an integral over an open set. And this is problematic. Integration, so the problem is that integration over an open subset of a compact, maybe I should just say integration on a manifold in general does not make sense. Just to use a very, very simple example, let's say you have an open interval from 0 to 1, and you have a continuous function. Well, if the continuous function stays bounded, then yes, you can integrate that function on the open interval from 0 to 1. But you could have even a smooth function, right? This can even be a smooth function that sort of like blows up or something, and it becomes infinite. And when you try to integrate it over that open set, things become unbounded and all that stuff, and it becomes unclear what that even means. So this is a problem. And so we're going to have to find a way to fix this. So this is what we're about to do. It's going to be a little bit ad hoc, but hopefully you will see the motivation that everything that we're talking about will hopefully be a motivation to make you see why we're taking this detour in order to prove this. So everything that we have said so far, that is not the proof. That's just a motivation for the proof and what we're about to do. So we'll take this down and we'll discuss something that's going to feel a little bit ad hoc. Actually, it's going to feel very ad hoc, but you will see the reason for why it's being done. So let's take this away and then begin again. Since the proof of Poincare duality comes down to integration, let us talk about integration again. So previously, and I'm not referring to this lecture, I'm referring to the lecture that we had that was about integrating on manifolds. We said that if X is a oriented manifold, it has to be oriented. Notice I'm saying that the manifold is oriented as opposed to orientable. Orientable means it could be oriented, and oriented means you found a consistently oriented atlas. The definition that we're going to write down will actually depend on the orientation that you pick. So if you were to take every one of your charts and you were to reverse their orientation, you will get the negative answer of what you had before. That is actually not serious whatsoever. It's just you're making a choice, and then everything just follows from the choice that you make. But in order for things to be well defined, it will be important that it could be consistently oriented in the first place. So let's assume that X is an oriented manifold, and we also assumed that it is compact. And let's also say that this is an n-dimensional manifold, and omega is a form of top degree. So the degree of the form matches the dimension of your manifold. Then we defined what it means to integrate the form over the manifold as opposed to over a chain. So integrating over chains, the fact that the manifold does not need to be oriented when you integrate over chains. But here, this is a different type of integration. This is integration on the manifold itself. And here you need the manifold to be oriented. I'm not going to get into the reasons for why that is. That was carefully explained in the previous lecture on integration. But a very quick summary is that to show that everything is well defined, it comes back to working with an atlas. And when you look at the change of coordinates between the atlas, you have to use the Jacobian. And it is important that the Jacobian stays consistently positive when you go from chart to chart in order to give you the same answer no matter what chart you pick. So that's like a very, very quick overview of why you need it to be oriented. But of course, if you want to see a reminder of that again in detail, you can just go back to that previous lecture and go through it again. So this is the way we defined it when the manifold was compact. Now the question is, can we drop this assumption? Can the manifold simply be oriented, and can we drop this assumption? Is there a way to do this? And the reason why we need to talk about this is because we saw that the idea behind Poincare duality is that we're going to integrate on open subsets of X. So even if X is compact, when you work on an open subset, it's not going to be compact anymore. And so you want to be able to extend the definition to be a little bit more general to handle those types of cases as well. So how do we then define this? And to maybe appreciate what we're about to do, let's keep everything simple, and let's take the easiest. Let's say we have a one-dimensional manifold, so dimension 1, and the simplest one-dimensional manifold that is not compact, which is going to be the real line. So the question here is basically, let's say we want to integrate on the real line, and we have a one form on the real line. So a one form would just be a function followed by dx. That would be your one form. And of course, the way you integrate this on the real line is because it's already Euclidean space. You would just ignore the differential, and you would integrate whatever that function is. So this is a smooth function defined on R, and you want to determine what that is equal to. So the thing with this is that in general, this integral does not exist. Because in general, if you have your function, it will probably do something like this. And if you try to integrate this over the real line, things become unbounded and all of that. So in general, this is not going to exist. But there is a special case for which this works out. And this happens when you have what is known as compact support. However, if the support of f is compact, then this integral exists. There's no problem in defining it. Let me quickly remind you what it means to be of compact support. So the support is the set of points in your space. In this case, our manifold is just a real line, so that f of x is non-zero. This is what you can say is the relevant part of the function. And then you would take the closure of that. So the picture that comes along with this is that, let's say your function is doing something like this. Then the support is where it is non-zero. So this would be the support. So this is where the function is non-zero, all the way up to the endpoints as well. That's why we take the closure. So that would be the support. And how would you integrate f over this? Well, because it is compact, if it's a compact subset of the real line, it is a bounded subset of the real line. And so it means you can enclose everything in a large interval. It does not actually matter what you make the a and the b, because if you just go further out to the left, it still remains 0, so it's not going to affect the integral. So you just make sure you enclose everything in a closed interval like this, and then it will then follow from here that this integral is equal to, and this you can even say by definition, this is the way you can define it. You can then define that this is the integral over the function over that interval. And then this is certainly not problematic because this is a continuous function. In fact, it is smooth, but it happens to be continuous, and you have a closed interval on which you're integrating, and in that case, there's no problem. So this is what we call a function having compact support. So maybe what I should say is that for those of you who might be interested in analysis, and I know that our course is not a course in analysis, but maybe you would find this interesting. In analysis, we often restrict functions, restrict our space of functions to smooth functions of compact support. So what I mean is that you can talk about all functions. You can even talk about all continuous functions versus smooth functions with compact support. So you have these two families of functions. And the problem with continuous functions or even smooth functions is that these functions do not always behave as well as you want to for the purposes of analysis. So like differentiation, limits, integration, and all of that. Whereas these functions, these are perfect for analysis. If you want to integrate them, there's no problem. If you want to consider the limit at infinity, which we often do in analysis, there's no problem. It's actually equal to exactly 0 and all that stuff. So in analysis, a lot of the times we restrict our family of functions to just be this family. And it turns out that this family is often sufficient. you are using fewer functions, but you have just enough functions that you can recover most of your information back. So for instance, if you've seen this before, you talk about the Fourier transform. That's what you call the Fourier transform. So if you have a function f, and f tilde is the Fourier transform, maybe you've seen this before. So if the function is written in terms of some variable, let's say x, you multiply it against e to the I, let's say yx, and then you integrate this and you're left with something in terms of y. So this is now a function in terms of y. The problem here, of course, is that because you're integrating from negative infinity to infinity, it's true that this is bounded because that's a complex exponential, but the integral might still not exist. However, if you assume that this is a smooth function of compact support, then beyond its support, this will be 0. And so this is actually an integral over a closed interval. And so you could make sense of this. So a lot of the times, so for instance, when you learn about the theory of Fourier transforms and things like that, one often restricts attention to functions of smooth functions of compact support, and you kind of work. I mean, I do not want to go off topic and talk about what you do there, but it's a very common technique in analysis that people realized that if you restrict everything to functions of this type, you can get a lot of information out of them. Maybe to use another example, so let E1, E2 up to En be the standard basis for Rn. And let's suppose we pick a vector in Rn. We can determine the vector, we can determine x by knowing what x does when you take the dot product with each of the basis vectors. Okay, in fact, x is equal to, so when you take the dot product with the basis vector, that is the coefficient when you write it in terms of the standard basis. So if you know, so basically what I'm saying is, if you have a mysterious vector, but I tell you what the vector is doing when you take the dot product with the standard basis, then you can recover the vector from knowing those dot products. And you can do something very similar with functions. So you can let's say, script f, this will be smooth functions of compact support, let's say on R, and let's say, okay, and let G be some smooth function in general. We do not assume it has compact support. Then you can take the dot product between G and F, where F is chosen from that family. So this is sort of like a dot product, right? You multiply them and then you sum. Now G does not have to have compact support, but these have compact support. And by multiplying them, this has compact support because it becomes 0 outside the support of F. And then you can integrate, and then you can ask what that is. And then you can ask the question, well, let's say you know what each of these are equal to for every F. Can you recover G from that information? In fact, that's kind of what Fourier analysis is all about. You're decomposing a function in terms of some kind of what plays a role of a basis, and then you try to reconstruct the function back from that. So it's a similar kind of idea, and that's the idea that you're restricting yourself to a space of functions which it is easier to work with. But we're not going to go there because that's analysis. That's not suitable for us, but I just kind of bring it up in case you're interested. So this is what we're going to say. So in general, if f is a smooth function on Rn, and it has compact support, and we often indicate it by putting a little c at the bottom. That just means the support of the function is compact. Then the integral over Rn of f exists. And the explanation is, again, very simple. Let's say this square is R2. I'm just going to draw the picture in 2 dimensions, and the support is compact. So let's say this blob represents the support of f. Of course, it does not actually have to be connected. It could be lots of different blobs like that. Because it has compact support, you can enclose it in a large enough rectangle, call it R, that contains it, and then you can just say that this integral is equal to f over the rectangle, and then you just integrate, well, you just integrate it over the rectangle as an iterated integral, and then you get your answer. So that's the way you would do it. So as you can see, that as long as something has compact support, then you can integrate. So now we're going to get back to manifolds. Let us generalize this to manifolds. Let X be an oriented n-dimensional manifold. We no longer assume that X is compact, and omega is a top form on X. Here, the degree of the form has to match the degree of the manifold. With the support of the form, so this is a subset of X, is compact. So it's a form of compact support. The question here is, of course, how do you define this? It's very similar to how you do it for functions, but here you have to be just a little bit careful because this is no longer a function, this is a form. I'm not going to write out the definition for this again because this was discussed in the integration lecture. So if you want to recall back what that definition is, you can just go back to that lecture again. But there is this analog of the support of the form. So now we're going to assume that the support of the form is compact. Then we can define the meaning of this. Because the idea here is that even though you are integrating over all of X, it's only the support that matters, and because that's a compact set, then everything works out in a nice way. So how does one do this? So as is very common, we first assume the support is sitting inside a single chart. So we first assume that the support of omega is contained in X lambda, where X lambda, where let's say we have phi lambda going from Rn into X, is a homeomorphism onto this open subset. This is an open subset of X. So we're assuming that the support sits in a single chart. This is a chart coming from the atlas. We're assuming we have an oriented atlas, so this is one of the charts. And then the way we do this is that we define the integral over omega is equal to, and this is by definition, you have to recall what a differential form is. A differential form is a collection of Euclidean forms in every chart. So you just find the local representation of omega with respect to that chart. So that's what we call omega lambda. This, by the way, is now in a Euclidean chart. So it's, I'm sorry, this is a Euclidean form. This is a form defined in a Euclidean chart. And now instead of integrating over X, you integrate over Rn. And the reason why this exists is because we're assuming the support is compact. Now, the definition of the support of omega, it is the way you define it, which I'm not going to do. It will follow from the definition that this has to be, will have to have compact support on Rn, and then you can just integrate that function. Well, technically what this would be is, this would be, how does omega lambda look like? It's some function, some smooth function, followed by the differentials. And the way you integrate this is you forget about the differentials and you just integrate the smooth function, the coefficient function. In a way, these differentials serve as iterated integrals, where you integrate f with respect to x1, then you integrate it with respect to x2, and so on. So this is what that would be. This exists because the support of this function will be compactly supported. So that's the way you do it. And this is well defined, because you might be concerned and say, well, what if it also sits inside a different chart? That's actually not a problem. And this is based on the virtue of the fact that this is an oriented manifold. I'm not going to go through the derivation again, why it comes out to be well defined in the end. That's done in the integration lecture, but that's the way you would do it. And now the question becomes more generally, how do you do this when you drop this assumption? So how would you do this? So, and now if we know how to do it in the special case, we can define how to do it in the general case by using partitions of unity. So then we would say that since the support of omega, this is a subset of X, is compact, this is a compact subset of X, and the collection of charts is a covering, this is an open covering of the support, it means, so this is just by definition of compactness, we can find, let's say, lambda 1 up to lambda m, so that the support of omega is contained in the union of this finite collection of charts. The next thing that we're do is we're going to use a partition of unity trick. So we're going to choose smooth functions. We're going to call this function alpha 1 up to alpha m. Maybe to make it easier, maybe I'll just call it, maybe I should just call it from x1 to xm, so that I do not have to use double indices. So we can find functions from alpha, we can find smooth functions, so these are going to be smooth functions on the manifold, so that the support of every one of these will be contained in xi, and the sum, if you add up the partitions of unity, that's why they're called partitions of unity, because they add up to unity. They add up to the constant function that's equal to 1 on x. Actually, I'm just realizing I probably want to be a little bit careful that we're not interested in x. We're really interested in the support of omega. So I really should say they add up to 1 on the unity function on the support. Okay, so that's what we're doing. And so what do we do next? So this part over here, we're just accepting the fact that you can do this. As we remarked, this has actually very, very little to do with topology. This has to do with analysis. It has to do with the fact that you can decompose the unity function in such a way. This is an analytical proof. So if we're willing to accept that, then here's what we do. Here's what we do next. So then here's how we integrate. We integrate x over omega. The idea here is you're basically putting in the function 1 times omega. That's the idea. You're multiplying it by the function 1. That does not change anything. So we want to define what the left-hand side is, and we're making the observation, whatever it is, it should be equal to this. But then 1 can be written as this sum. Now, it's true that you're decomposing 1 on the support of omega, but it's only the support of omega that really matters here when you integrate. So you would then say that this should be equal to the integral of the sum of all of these. And that should be equal to, so when I keep on saying it should be equal to, what I really mean to say is, however we define the left-hand side, it should be, like, if it has the properties that we want it to have, and integration has the properties that we want it to have, then everything's going to be forced on us, and the thing that we get at the very end is going to be the definition of this thing. So this should be, therefore, be equal to, integration should be linear on sums, right? That's a property that we're used to. So this should be the sum. And here you do integration of x alpha I omega. And the reason why this is nice is because when you multiply omega by alpha I, notice alpha I has its support contained in a single chart. And then we know how to do this. Okay? because this is previously what we've talked about. How do you integrate when you have a form whose support is contained in a single chart? That's the special case, right? So what we basically do is we forget about the steps in the middle. We kind of delete this, and we just say that this piece is equal to that piece, right? This is the way mathematics works, that you delete the motivation, and the thing that you get in the very end becomes the definition. So that becomes the definition. So you define the integral of your form is what do you do? You first have to cover it by a finite collection of open sets in the atlas. You choose a partition of unity for that covering, and then you define that in this way. And now it requires some verifications. The first verification you need to show, of course, well, I guess there's only one thing you need to show, is that you have to show that this is well defined, that you are making choices. The first choice that you're making is you're choosing what covering that you're using. Maybe there's a different covering, but that is handled by the special case that if it falls into two different charts, it will not matter. And then the other one that you have to also justify is that if you choose a different partition of unity for that very same covering, then the answer you will get in the end will be consistent with the previous one. And that requires a verification. It's actually a very interesting proof. It's not as hard as it seems. Like it really does seem like that's very hard to show. It's really not as hard as it seems. It's like a paragraph proof. You can find it explained in the Breton book, for instance. It's a nice proof. Basically, just to summarize how it goes, is you have two different coverings, right? You have one covering, you have another covering, and the trick is that after you write this integral like that, you then you multiply this by 1, and then you use the other partition of unity to insert that in there, and then when you do it the other way, you can do the same trick in reverse, and then you see that they end up giving you the same answer in the end. So basically what I'm saying is that if you have two different partitions of unity, alpha I between 1 and m, and you have beta j between 1 and some number, let's say k, then what will end up happening is that regardless of how you do the integration, you will end up with, it's a sum over I and j, integral over x, alpha I, beta j, omega. And in this case, it's clear to see that you end up getting the same answer no matter how you do it. That's a very quick overview. In fact, maybe you can even do it yourself as an exercise if you want to challenge yourself. But basically, you can show that whatever that is, it can be further written like this. And then in the end, it does not matter what partition of unity you use. It will always lead to the same answer. So anyway, this is the way that you do it. So we have defined, so let's just go back and see what we did. We have defined as long as the manifold is oriented, and as long as omega has compact support, so the way we would write it is like this. We'll remove all of this. So this is no longer necessary. This is the explanation for how we do it. So the notation that we would use is we would say that as long as the form has compact support, then it is possible to define the integral of the form over the manifold. The manifold does not have to be compact, but the requirement would be is that the form should be compactly supported. So this is the way you can generalize integration just a little bit, but that would be sufficient for our purposes to prove Poincare duality. So then now we have to talk about something else. There's something else we need to discuss before we can get to the proof of Poincare duality, and that is, this is called cohomology. Well, it's called compact. Or maybe I should say cohomology with compact support. This is going to come up because, as we were just talking, when we can integrate forms as long as their support is compact. And to set up this different cohomology theory, it would be helpful to go back to Euclidean space. So let's just recall that, let's say U is an open set in Rn. And this is what we always do. Whenever we want to understand how something works on a manifold, we always understand how it works on Euclidean sets, and then we piece them together coherently and get something globally defined on the manifold. So let's go back to Euclidean spaces again. We pick U, an open set, let's say non-empty, and then we define and then we construct we construct something that we call a co-chain complex, which it goes up. So you talk about 0 forms on U going into 1 forms on U, into 2 forms on U, and so on. This is the derivative operator that brings them up. And omega k of U, that is equal to, by definition, so this would be the algebra of smooth functions. So this is the way you would write it. So you would look at smooth functions. So those are going to be the coefficients. And it's the algebra that's generated by these symbols, dx1 up to dxn, with the requirement that if you multiply them together, and here multiplication is denoted by the wedge operation, then that gives you the negative in the other direction. Okay, so that is how you define differential forms. So the coefficients, it's just like a it's very similar to a polynomial algebra, except the coefficients are smooth functions and they satisfy this relationship. Okay, so this is how you define these. And then the derivative operator d, exterior differentiation, it brings you up a degree. Oh, I forgot to say something. I should have said that this is the way you define the differential algebra. And then this is just going to be the subspace, the subset, whatever you want to say, subset of this algebra, so that these have degree k. So that just means that you're choosing k of them. That's all what that means. So this is your differential algebra, and then you choose a smaller collection that has degree k. So this is the way this is defined. And then from here, you can talk about cohomology. Now, cohomology with compact support, it's actually very similar, except instead of considering smooth functions, we want something that we can integrate. And so we're going to restrict everything to compact functions of compact support. So these are going to be smooth functions whose support is contained in U. So that would basically mean that if this represents U, then the support of U will be a compact subset of that. And that would mean that your functions, they're 0 outside this red region, and they're, yeah, that's what that would mean. So it's a smaller collection of functions, but it's very similar. And you call this I guess you can call this the differential algebra with compact support. That's all what you're doing. And what you need to realize is you still have a cochain complex, just like you have before, for the simple reason, because if you have a function, a coefficient function, that vanishes outside this red region, then its derivative will still vanish outside this red region. So if you were to take such a function and you were to find its exterior derivative, it will still have compact support. So for these reasons, one has, you can say, a compact cochain complex. So this is what you would have, and then you can talk about the collection of forms with compact support of degree k. And from there, you can define compact cohomology in exactly the same way as we've done before. And then you can generalize this to manifolds. So to generalize this idea to manifolds, we let phi lambda be an atlas. So every phi lambda maps, let's say, Rn homeomorphically onto an open subset. This is homeomorphically onto an open subset of X, so that these open sets, they cover your manifold. And then, so by definition, so we make this definition that omega is, let's say, a K-form of compact support, if and only if, and you can probably guess what this means. It would just mean, this is just like it works with differential forms. This is just a collection of Euclidean forms where each omega lambda is a K-form on Rn, but with compact support. And this collection is coherent. So this is the way you would define how you would generalize this idea to a manifold from Euclidean space. So you know how it works on Euclidean spaces, we know what that means, and then the idea is that on a manifold, it's just local representations of your form so that they fit together in a nice coherent way. Now I want to show you an interesting example. So here's like an interesting example. And I'm going to do this very simple. We're going to do this in one dimension, and let's do this on the real line. Because I do not want to do this on a circle. Because if you're doing this on a circle, then cohomology and compact cohomology, it will be the same thing because the circle is already compact. So let me just make a remark. So note, if X is compact, then if you were to calculate the ith cohomology of X, that would actually be the same exact thing as the ith compact cohomology of X. Because everything is compactly supported, because X is already compact. So the distinction will lie if you pick something that's not compact. So let's say the real line. So we're going to do this on the real line. So let's look at this. H0 of the real line. This is a one-dimensional vector space because the real line is connected. But if we're going to do this by definition. I mean, we already know this, but to do this by definition, basically what you have to realize is you're picking a zero form. So a zero form is a function. So what if you pick a smooth function on the real line? And if it's in the cohomology, then it means its derivative will have to be 0. But what is the derivative here? Well, the derivative here, this would be the derivative, the ordinary derivative of the function, and then dx. So x represents the it's just a coordinate, right? It's just you give me a point, x represents the location of the point. So this is just a symbolic differential here. And if this is equal to 0, it means that f prime is 0, so the function has to be constant. So functions that are in the zero-dimensional cohomology will consist of constant functions. So for every constant you have a function, and so that's why it's isomorphic to R1. You have to understand these are two different R's over here. This is a manifold. You're thinking of it as a smooth manifold, whereas this R, you're thinking of it as a vector space. So there's two different, it's the same R, but it has two different meanings here. Okay, so now what happens if we look at the one-dimensional, well, actually, let's see what happens if it's the compact cohomology. This will actually be the zero space. It gives you a different answer. Let's understand why that's the case. So for the same reason as before, if we pick a zero form, this is a smooth function, and we're saying its derivative has to be 0. If it's in the cohomology, its derivative has to be 0. It's in the kernel. But if the derivative is 0, then that means, as before, f prime dx is 0. So it means f prime is 0, which means f is a constant. Now here's where the issue occurs. It has to have compact support. If you pick a constant other than 0, the function is not going to have compact support. If you draw, let's say, f is equal to 1, then this is the graph of your function. Notice it does not have compact support on the real line. And that's where the problem is. So the only constant function with compact support on the real line is just the zero function. So for this reason, the compact cohomology actually gives you a different answer. Now let's do the first dimensional homology. So H1 of R, that would be 0. Why is this? So here's the reason why that is. So we have to pick something we have to pick a one form, and one form will look like this. And note, so if omega is f dx, then the derivative is automatically 0. The reason for this is because you only have one symbolic. And when you differentiate omega, what you would get is you would get d omega is f prime dx wedge dx. So it automatically becomes 0. So anything of this type will automatically have 0 derivative. So it is a representative, it is a class. Well, it's a representative for a class in the first dimensional cohomology, and we claim that this is trivial. So this is just a class, right? So technically we should say a class, but I'm going to be sloppy. This is a representative for a class, and we claim that f dx can be expressed as the derivative of something. And if it can be expressed as the derivative of something of one lower dimension, in other words, if this has an antiderivative, then it would mean that it is cohomologically trivial, and so this really represents the 0 class. So why is that the case? Well, the reason why that's the case is very simple, that so we have our function, so here's what we can do. We can say that f dx is the derivative of g. So we need an antiderivative, and one way you can get an antiderivative is you pick an arbitrary base point. So let's say g of x is the function. So it's the integral from an arbitrary base point, let's say 0, it does not matter, from 0 to x, and then we integrate the function. And then by the fundamental theorem of calculus, if we take the derivative of g, it will give you back f. And so from here we get g prime dx, so we get f dx. So as you can see, that if you have a form of this type, it can always be expressed as the derivative of a smooth function. And you can pick different base points, and they will result, it does not matter. I just picked 0 for convenience, but you can pick other base points. This is still true. And for this reason, the one-dimensional cohomology would be 0. And then one can also then check that the higher dimensional n of R is 0 for n bigger than or equal to 2. However, something very interesting happens when you get to compact cohomology. However, the compact cohomology, the one-dimensional cohomology of R, that would actually be isomorphic to R. So yeah, you're getting a different answer. You should see this, that ordinary cohomology is one-dimensional, and compact cohomology is 0-dimensional. But when you get to the one-dimensional cohomology, you get something that's 0, and the compact cohomology that's one-dimensional gives you R as the vector space. So why is that? So here's what it has to do with. So let f dx be a representative in this cohomology. So in particular, it means the support of f is compact, right? Because what does it mean to be in the compact cohomology? It means that the differentials, the coefficient functions that make up the differentials, they have compact support. So the support of this function must be compact. Now, what happens when we try to go backwards? So is it true? So is it true that f dx is the derivative of something? Can we find the function that will give us the derivative of that? Because if we can, then that would imply that each of these representatives for classes are cohomologically trivial in the compact cohomology. And so they just represent the zero class. And then for the same reason as before, the compact cohomology would also be trivial. But you're going to notice something interesting that happens. So let's construct this. So let's define the following function. So I know that previously we defined the function from 0 to x of f, but this time let's do it a little bit differently. It's convenient to just make that be negative infinity. It does not matter what you pick, but it's just going to be convenient to make that be negative infinity. And the reason for this, it has everything to do with the fact that you have compact support. So here's like a picture for what's going on. Let's say your function does something like this, f. And then you're picking negative infinity all the way out there. So as you can see, that the integral will exist precisely because the function has compact support. Actually, it does not matter. You can move this around, but this is just convenient to leave it like this. And then the derivative will still be f. But here's the main question. But is it true? And this is really the crucial point. But is it true that g itself, that the support of g is compact? Will that be the case? Well, you can see from this picture, I mean, what happens as we go out to infinity? You can see that the limit at infinity would just be this integral. So if this integral is 0, then g has compact support. It actually requires a little bit of justification to show this, like this part over here. It does require a bit more of a proof than what I just said, but it's not too difficult to understand this. If you just look at this picture, for instance, if you look at this picture, what happens when you integrate from negative infinity up to x? So how would the function g look like? So the function g, it starts off as 0, so it will be 0. And then when you get up to here, you pick a positive area, right? You pick a positive area, and then it plateaus and it becomes constant. So the function g, when you integrate, it will kind of go up, and then it will plateau and it will become constant. The problem is that, as you can see, this function does not have compact support. It does not return back down again to 0. So if, however, your function is of a very special type, that it just nicely integrates, let's say something like this, that it nicely integrates to 0, then that means the area will go up or go down depending how the function looks like, but it will then return back to 0. And so then the actual picture would be that maybe the g would go something like this, perhaps. That would be g, and then the support will also be compact. So here, you actually have to be very careful that it is not automatically true that every one form is the derivative of a function. It's important that the function that you're working with, not only does it have compact support, but its integral from negative infinity to infinity has to integrate to exactly 0. So what's the point of all of this? So what we're saying is basically this. So if f1 dx and f2 dx are two representatives of classes in the compact cohomology on the real line, and they integrate to the exact same number, then their difference, so that's their difference. So if we want to show that these are cohomologically equivalent, we take their difference and show that their difference is the derivative of g, where g is the difference, where g is the function. Maybe we should write it like this: g of x is this function. And the reason why this works out is because this function, it now integrates. So then g is a smooth function of compact support, since you can say g at infinity, since the integral over the whole thing gives you 0, because these are now equal to each other. So as you can see, that the cohomology class is determined by the integral. So thus, the compact cohomology class of f dx is determined by its integral on the entire real line. If its integral is 0, then that means this is the trivial class. And if the integral is equal to, let's say, 2, and then integral of a different one is equal to 3, then those two will not be cohomologically equivalent to each other. So that's what it means. And because of that, it's determined by the integral, and the integral is a real number. We see from here is that the compact cohomology of the real line is actually R. Okay? And there is a Poincaré lemma for all of this. So let me take this down and say the Poincaré lemma. So these are the Poincaré lemmas. Poincaré lemmas. So there's two versions. The first version we used when we proved the Rham theorem. So this says that if C is an open set in Rn and it's convex, I should say non-empty. I realized that previously I did not mention that it's non-empty. I should have actually been a little bit more careful about that. If it's empty, then the cohomology will be trivial in every dimension, just simply based on the fact that you do not even have any smooth functions. Is not empty, then the Poincaré lemma says that the k-dimensional, or let's say the i-dimensional cohomology is isomorphic to, so there's two cases. The first case is it would be R if I is 0, and it's 0 if I is not 0. And of course, if it is actually empty, then it would be 0 in every dimension. You can carefully think it through, but it just basically has to do with the fact that if you have the empty set, and you talk about smooth functions on the empty set, then you do not have any functions. You do not have any smooth functions there. Just all of them are just 0 spaces, and then you have a cochain complex consisting of just 0 spaces. So it's something that I guess I should have been a bit more careful with last time, but fixing it right now. So this is the Poincaré lemma. And then you have the other version of the Poincaré lemma. If C is open in Rn, it's convex, not empty, then the compact cohomology. So there's two different C's, of course. This compact, this is convex set. Then this one would be isomorphic to. This one goes a little bit differently. And the example that we just did with the real line is just sort of a hint in this direction. Of course, that's not a proof. But this one would say that this is isomorphic to R if I is equal to N. So here, if the I matches the dimension, that's actually what we had on the real line. This was H1 and this was R1. So they match. So if they happen to match, then it would be R, and otherwise it is 0. And I'm not going to prove this. So the proof of this is in Breton. The proof of this, I'm not sure if it's in Breton. I did not check. But it's definitely in Bot N2. Of course, it requires justification. The proof is actually somewhat similar to this, except this is a little bit trickier because you have to focus on the integral and whether or not it integrates to 0 or non-zero and things like that. So these are the Poincaré lemmas. And now I want to talk to you about the Mayer-Vietoris sequence. That's the other thing we should talk about. Because we're going to have a Mayer-Vietoris sequence, but it will be a little bit different. So there is a Mayer-Vietoris sequence for compact cohomology. It's going to be a little bit different, though. So let's just recall the regular Mayer-Vietoris sequence. So let's recall if we have a manifold that's a union of two open sets, we have the following sequence. So this is just a fragment of the sequence. So we talk about hi of x, then it goes into hi of u plus hi of v. And the way this works is you pick your form and you map it by restriction. You restrict it to u, and then you restrict it to v. That's the way you do it. I'm not going to go over what it means to restrict a form to an open set. We've talked about that before, but just going over that part. And then here you have another one. This is H I U intersect V. Okay, U intersect V. This is the one that, so you pick a form in here and a form in there. So you pick a form in here, let's say omega 1, and a form in here, omega 2, and then you send it over. You restrict to the intersection. You restrict the other one to the intersection, and then you subtract. Of course, this is an arbitrary choice to make this first, this be second, and then it gets fixed by the fact that the next one, this is the tricky one, which we're not going to go through. This is the one that uses partitions of unity. I'm going to just put a question mark over here. I do not want to go through that construction again. This one is a bit trickier to explain, but this is the one that increases the dimension. Basically, the way it works is if you have a form on the intersection, you use a partition of unity to split it so that each of the two pieces are supported in U and V, and then you take each of those two pieces and you take the derivative of both of them, and then you go up there. But oversimplified. But that's the way you would do it. So this is the Mayer-Vietoris sequence. And the thing about this is for compact cohomology, the above sequence would not make sense. Would not make sense. Why not? So let's just look at this one right here. X is a union of two open sets. So you have U, you have V, and they happen to intersect. So you might be thinking, do you have a Mayer-Vietoris sequence where it's sort of the exact same sequence, but you just decorate all of them by just putting a little C subscript on every one of them? And this is where you're going to have a problem. You cannot do that. Let's see why not. So if we're just going at this first mapping, you have something that has compact support. So if it has, let's say, compact support, let's say this is the support. Say this is the support. Notice what happens if you were to restrict, if you were to take your form and you were to restrict it. Right? What would happen if you were to restrict it to, let's say, U? What would happen? Well, what would happen is you would cut all of this away, right? So maybe I can do this for you. I'm going to remove this. You're going to cut all of this away, and then you will be left with something that goes like this, and then you're kind of missing that part of the boundary. So if these represent, let's say, regions in Euclidean space, then we know this cannot be compact because it's not a closed subset of Euclidean space. So something is not making sense. This is very suspicious. This is not necessarily something that has, this is not necessarily a compact subset of U. And that's where the problem lies. So we're not allowed to do this. That does not work. So instead, we have to do something else. So here is the modified version of Mayer-Vietoris sequence. So this is the way you would have to do this. This might look a little bit strange, but we're going to start with this one instead. So we're going to start with HI, U intersect V, and we can send it into HI of U. So this is with this is compact cohomology this time, like this. And let's explain how this one works. So you're going to pick a form that has compact support contained in the intersection, and you're going to map it to, and this is going to be something called extension. I'm not going to, for lack of saving time, okay, because I do not want to get off topic and make this lecture be too long, I'm going to try to give you the intuitive idea of what you're doing, and then, like I said, this lecture, there's a lot of little pieces that one has to fill in, but the idea, I will give you the whole idea. You just have to fill it in. So this is going to be like one of those small little things you have to fill in. So this one is extension. So instead of restriction, I'll write it like this. I'm going to write it in a simpler way, but I'm going to put it as a superscript. So this just means extension to a larger set. So let me draw you a picture. This is U, this is V, and we have a form that has compact support on the intersection. So let's say this is the support. The idea is that outside this red region, everything becomes equal to 0. So the extension to U means it's the exact same form, you just make it be equal to 0 all the way out here. The reason why you can do it is precisely because U, it becomes 0 in a smooth way. You see, the issue is if you have a function, and I want to extend my function beyond the domain, and I make my function be equal to 0, well, the chances are you introduce a discontinuity. But if my function smoothly goes down to 0, and then I just extend it to be equal to 0 beyond its domain, because it is already 0, there is no problem with just extending it to be 0 outside that piece. So that's basically what that means. I will leave it up to you to try to figure out how you make this rigorous, like how do you rigorously define the extension operation. But the reason why this works, you see, this is quite interesting. It does not work for the original Mayer-Vietoris sequence, because in the original Mayer-Vietoris sequence, if you have a smooth function, let's say, and you extend that function to be 0 beyond its domain, chances are it will probably not be smooth anymore. But here, because these forms have compact support, by defining them to be 0 in all of beyond the domain, it moves smoothly into 0, and that's the reason why you can get away with it. And then you just make it be 0 out here as well. So that's the way you would do it. And then how would you then map this into X? How would you do that one? Well, it's actually very similar. You can probably guess how you would do it. Let's say you have omega 1 and you have omega 2. These are two representatives. And the way you map it is you take both of those forms, you extend them to X, and then you subtract. That's the way you would do it. And then you may wonder, well, what's the next one? The next one is, so the next one, I'm going to skip this one. This is a bit tricky to write out. But the next one, you would go up a dimension because you're going to use the derivative operator again. And then you will return back to the intersection. The way you do it is very similar with partitions of unity. You basically introduce, the way you would do it is you would introduce partitions of unity. If you want to see it, you can just look at the Wikipedia page. Maybe I can even show it to you if you really want to see how to do it. Let me show it to you. So if you want to actually see more details to that. So it's on the page for Mayer-Vietoris sequence. And there's different versions. There's a version for homology. Then they explain to you what is known as the boundary map. This is the lowering of dimension map, which is the tricky one. Then there's a version for something called reduced homology, which we never talked about. They give you an application with the sphere, the Klein bottle. We actually did some of these before in class. And interestingly, they also have cohomological versions. This one is not applicable to us. This is cohomology with coefficients in the group. That's not something we're talking about. This is the one for differential forms. Oh, it looks like I cannot find it. I did see something like this before. Is it under differential forms? I'm not sure. It's strange. I thought I saw it somewhere. So I cannot seem to find it. Oh, okay, so here it is. For DRAM cohomology with compact support, there is a flipped version. So the reason why they call this a flipped version is because, as you saw, it goes a little bit So there it is. This is the theorem cohomology of a smooth manifold. This is what we were saying. You're going from Hn of x to u and v separately, then the intersection, and then from the intersection you go up a dimension to x. And you're using, as you can see, partitions of unity to do that. And the reason why we call this the flipped version is because you can see it goes a little bit differently. We're going from the intersection to u and v separately, and then from u and v separately into x, and then from x we go up a dimension into the intersection. And they explain to you how to do it. So they call this, so delta over here, this is the sign inclusion map, where this is extension, and then you subtract. Well, actually, you see that they're not doing it the way we're doing it. Their delta is the sign inclusion map, whereas our delta is just the inclusion map. It's just a question of where you choose to put the signs. We're doing this as the diagonal map, and then the sigma over here is the difference, whereas for them, the sigma is the sum, right? It's not that serious. It's just some arbitrary choices. But what is this D star map? This is the one that's a bit trickier to define. You can kind of see it written out over here if you want to. And this is the one that uses partitions of unity. So how you go from x to the intersection. So anyway, that's the Mayer-Vietoris sequence for compact cohomology. So there it is. So as you can see, the important part here is that it is flipped. It is flipped. It goes x. So the original Mayer-Vietoris sequence, it goes x, separate, intersect, and then x. This one goes intersect, separate, union, and then intersect. It goes a bit differently, but it's not. It's actually different from Mayer-Vietoris sequence for homology, because the Mayer-Vietoris sequence for homology, not only does it sort of follow this rule, the difference is the one that is next over goes down the dimension. This one goes up a dimension. So it is different right there. So this is what we call the Mayer-Vietoris sequence for compact cohomology. You have to actually verify that this is an exact sequence and all that stuff. But again, those are the more minor details that one has to work through. And with all of this, we're finally in the position to prove the Poincare duality theorem. And that's what we're going to do now. We finally have all of the tools to prove Poincare duality. All of the stuff we've said before, that's really the build-up to the proof. We have the tools to prove Poincare duality. And this is the way we're going to state the theorem. Let X be a oriented manifold the natural map, and this is in fact a linear map. It's a map between vector spaces. The natural map that takes you from the ith, maybe we can say an n-dimensional manifold, that takes you from the ith cohomology of X. There's a map that takes you to Rham, so this is the dual. And this one is going to be n minus I of X, but here we put compact support cohomology. So that's the dual of the compact support cohomology. So there's a natural map between these two vector spaces. Showing it's a natural map is the easier part. That is up for you to check. The more important part is to verify that this is indeed a isomorphism. That's going to be more important for us. That's what we really want to prove. But there's a natural map, and how is this map defined? This is what we've said before, that if you pick a form, a representative in the ith cohomology, you map it. So here, you're going to pick a form of compact support, and the form has degree n minus 1. Let's call that form eta. And since it's assigning a form to a homomorphism, it has to tell me how a form is being assigned to a real number. and it's being assigned by integrating over x, and then you do omega wedge eta. It does not matter what order you choose to wedge them. It's just going to be a different map, possibly a different map, but it's not going to matter. It's still going to be, will give you the isomorphism in the end. So this is what we have. So we have a natural map that takes form and it assigns it to this homomorphism. By the way, this is why we need to have compact, a form of compact support, because by taking the wedge, omega itself does not necessarily have compact support, but by taking the wedge with eta, this product now has compact support, and therefore the integral exists. The integral will exist because this is an oriented manifold, so that's the way so the integral is well defined. So that's the way that you do this. But so far, this is not the theorem. Like, the actual theorem is that this is an isomorphism, and this natural map is an isomorphism when x is compact. Actually, if you look at the Bott and Tu book as a reference, they tell you that x does not even need to be compact. It is true in general, but that is more difficult to prove, and they do not really prove that more generally. The complication arises that when x is not compact, this can possibly be an infinite dimensional vector space, and this could be an infinite dimensional vector space. So things do become a little bit trickier because these cohomologies might become infinite dimensional. And there's all sorts of tricky things that might happen, but it happens to be true more generally. For our purposes, we're just talking about compact manifolds anyway. So the fact that this is so it's always a natural map. That's not a problem. But we're arguing that this natural map is actually an isomorphism, but we're going to prove it's an isomorphism in the case when x is compact. That would be sufficient for what we want. And what's the corollary from this? So as a corollary, so this is Poincare duality. So this is the way Poincare duality is actually stated. And now we have a corollary from all of this, and that is if x is compact and oriented, of course, then the compact cohomology is the same thing as the ordinary cohomology, because the space is already compact. Everything will have compact support. So what's the implication from here? So thus, the vector space, this space, which is finite dimensional, is isomorphic to the dual of this one. But the dual of a vector space is isomorphic to the vector space itself. But this is not, as we said, this isomorphism is not natural. This one is not natural. This one is natural. Natural, to quickly remind you what that means, is that it's a type of mapping that preserves commutative diagrams for you. This is going to be important for us when we prove the theorem, as you will see. As you will see in the proof of the theorem, this is why this is going to be important, that this is not just an isomorphism, it's a natural isomorphism. So even though it is true that this is isomorphic to that, they're not isomorphic in a natural way, and this is why the theorem is stated rather with the dual. That's the way it gets proven in the actual theorem, as we're about to see. So it therefore follows from here that lowercase hi, which is the dimension, right? This is what we call the Betti number. The Betti number. That's the dimension of the cohomology. And as we remarked intuitively, this is counting the number of holes you have in your space of dimension I. That this is equal to that Betti number. And this will complete the proof of Poincare duality. So this is the way we stated it at the beginning of the lecture. So the remaining question here is, how do you justify that when x is compact, that this is an isomorphism? So that's what we have to work through. So let's take down the corollary, because that part is straightforward, and focus on Poincare duality. And of course, one does have to check many things here that are left to the reader to check. For instance, one of the things you have to do is you have to verify that this is actually well defined. What if you choose a different representative? Then exactly as in the proof of the de Rham theorem, the reason why it's well defined has to do with Stokes' theorem. But this is the other version of Stokes' theorem. This is the version of Stokes on manifolds rather than on chains. So it's the other version. But it happens to be true. Okay, so this is what we have here. And this is what we want to prove. So how do we prove this? Proof. So let's make this observation. So observe that if C is an open subset of, well, how about we just call it U? I do not like calling it C. Let's call it U. Is an open subset of Rn. This is non-empty convex. Well, actually, it could be empty. I mean, if it's empty, then it's going to be true for trivial reasons because both of these are going to be 0. So is a convex, then the map from the ith cohomology of U to the dual of the n minus I compact cohomology of U, so the dual, that this is an isomorphism. So why is this an isomorphism? So this follows from the two Poincare lemmas. This is what we just talked about. There's two versions of the Poincare lemma, one for ordinary cohomology and the other one for compact cohomology. So you have to basically go through cases. So you have to consider what happens when, so the interesting thing happens when, so you have to basically consider when I is equal to 0, when I is equal to n, and when I is different from 0 and n. That's what you have to go through. So let's maybe look at the easiest one, and this is when I is different from 0 and n. So if it's different from 0 and n, then by Poincare lemma, this one is 0, and this one is 0, right? And the dual of the 0 space is the 0 space. And so the map from 0 to 0 is automatically an isomorphism. So that's not a problem. And then the same thing happens, yeah, so when it's different from 0 and n, this is no problem. The other thing we need to consider is what happens when I is equal to n. So when I is equal to n, assuming that n is a positive number, positive integer, then this one is going to be 0. And the 0-dimensional compact cohomology of U by the Poincare lemma is also 0. And you have the dual of 0. So this is again an isomorphism. And finally, you consider what happens when I is equal to 0. Right, when I is equal to 0. Okay, so in this case, this one, the 0-dimensional cohomology is R. This is isomorphic to R. And the compact cohomology, this is the n-dimensional compact cohomology of a convex set in Rn. So by Poincare lemma, this is also R. So this is the dual of R. And the dual of R is isomorphic to R. So you have a map from R to R. Now, a linear map from R to R is automatically an isomorphism, provided it is not the 0 map. So you just have to explain why this is not the 0 map. And all it comes down to is understanding that 0-dimensional cohomology, and this is compact cohomology, that this is just smooth functions. And basically what you're doing is you're taking a smooth function and you're assigning it to something in here. So take the simplest smooth function you can think of, and it's the function that's equal to identically 1. And then that function will then give you something in the dual, so something that will take an n form and will map it by integrating it over x, the constant function 1 integrated over eta. So then you just have to show that you can find the existence of n forms that do not integrate to 0, which is not a problem. That's basically calculus. You just have to show, right? Think about this. Integrating over x, in this case, integrating over u, right? This is no problem whatsoever. You can easily imagine, right? If you have a convex set, you can easily imagine that. So like, for instance, like let's say your convex set U is something like this. Okay, so you just put, let's say, a square inside U, and then you create something that is positive on that square, and then it plateaus down to 0 away from that square. And then it's clear that when you integrate that function over U, it's going to give you something non-zero. So it's not going to be the zero mapping. So this is just calculus, right? The fact that this is not the zero map is calculus. So since this is not the zero map, the only other possibility is that it's an isomorphism between these two vector spaces. So I'm going to remove all of this. And the observation here is simply that the isomorphism is just coming from the Poincare lemmas, and that's why we needed to state those lemmas, and that's why they're called lemmas, because they're used in these types of proofs. Okay, so what do we do next? So the next thing that we do, and this is what we're going to, since X is compact, we can cover. So we can go ahead and cover X by open sets. Let's call them U1, U2, U, let's not call it N, let's call it something else. Let's call it M. So these are open subsets of X, so that each UI is homeomorphic, or you can say diffeomorphic, does not matter, is homeomorphic. The reason why it does not matter is because if two things are homeomorphic and you have a smooth atlas on one thing, you can use the homeomorphism to map over the smooth atlas onto the other one. That's why it's not a big deal which one you call. So that each UI is homeomorphic to a convex open subset of Rn. Okay, so we have this, and this is where the other part that we're going to also assume. And we're also can construct. We can also construct UI in such a way, this collection, so that any intersection of them will be homeomorphic. It could be empty, but it could be homeomorphic to a convex open set in Rn. So this part, this is the part where we actually had this happen again before. So what are we saying? We're saying that here's our collection. We're saying that each of these are homeomorphic to convex open sets in Rn. But maybe these two, the intersection of those two, the intersection of these two, maybe the triple intersection of them, maybe the intersection of all of them, and so forth, that no matter how you intersect them, they will, I mean, it could be empty, in which case it's automatically convex. It's just empty set. And of course, this result is true for the empty set, because this is 0 and that is 0 automatically. So all of these are homeomorphic to convex sets in Rn. Now, why can this be done? So this is what we've said before. The justification for this step is geometrical. Is geometric. We pick UI to be what is known as geodesically convex. And geodesics only make sense when you put a geometric structure on your smooth manifold, which can always be done. So this is something you will learn in a differential geometry class. So if this bothers you, this is a well-known fact in differential geometry. You would use this a lot. So it's not a big deal. It's just something that might be new right now, but it will make sense in the future if you go on to study differential geometry. So that's what we have. So you can kind of accept that there's a way to do this, and if it bothers you, the way you justify that is through an interesting geometric argument that has to do with geodesics. So that is how we're picking these sets. And yes, so how do we proceed from here? So this is how we're using compactness, that we have a finite such collection. And here's the observation. So here's the idea. The idea is that Poincare duality is true on each U. Maybe I should not call it UI. Maybe I should call it UJ for each U in this collection. By the lemma, by the Poincare lemma. Right? That's what we said, because each of these is homeomorphic, right? This map is an isomorphism by the Poincare lemmas, and each of these sets, they happen to be open sets in X, but they're homeomorphic to a convex set in Rn, and we have this result. So we have that isomorphism. So the observation here is Poincare duality is true. So what do we mean it's true? So in other words, i.e., that we have natural isomorphisms. From H I of U to the dual of in the compact cohomology. That these are isomorphisms for every single I. Right? This is an isomorphism for every I. And then we're going to use Mayer-Vietoris sequence to glue this together. Next, we use the Mayer-Vietoris sequence to glue this together. What do we mean? In other words, i.e., that if you give me a union of any two of them, let's say you have UJ union UK. Actually, let me do it like this. Maybe not to use too many indices. Let me write like this. U union V, that we have this map into the compact cohomology of U union V for any two U and V in this collection, in this finite collection. So we're going to show that we know that these are isomorphisms on each of these individually by the Poincare lemma. Then we're going to use Mayer-Vietoris sequence to show it is true on their union. And then you kind of repeat the argument. So it's basically like a proof by induction. This is why you need this to be a finite covering, because by doing it, you eventually exhaust everything and you fill it up. If you're wondering how you would justify this if you have an infinite collection, Bredin actually does talk about something like that. You have to use this notion of direct limits. There's a notion in algebra called the direct limit, which we really do not want to get into. That's just unnecessary for us. But we're just doing it in the compact case, so we have a finite number of open sets. And once you see how you do it for just two, you kind of just keep on repeating the argument, building upon that. And as you keep on taking the unions, eventually when you take the union of all of them, you get X. You get back to your manifold X, and you've justified the theorem. So here's how you do it. Okay, so we have two Mayer-Vietoris sequences. So we have two because we have two different cohomologies, ordinary cohomology and compact cohomology. So when we use ordinary cohomology, this is what we get. We get HI U union V. Then we could map this to HI of U plus HI of V. Then this goes to HI of U intersect V. Yeah, like this. And then over here, we have H I minus 1 U intersect V. And we have one more, H I minus 1 of u plus h I minus 1 of v. So this is what we have, right? Mayer-Vietoris sequence. From the intersection, we go to the union, and the degree increases from I minus 1 to I. Then from the union, we split it into a sum, and from the sum, you can restrict it down to the intersection. And below this, we have the other Mayer-Vietoris sequence, but this is the Mayer-Vietoris sequence that, and we're going to do this using n minus I, right? Because the whole point here is that we're relating this one with that one. So now we're going to write down the Mayer-Vietoris sequence using this one. So this is going to be U union V, and it's going to go, so here the distinction would be that this one will increase in degree, n minus 1 plus 1, to the intersection. And then from the intersection, it gets split. It will then get split into a sum. So this will be V. So this is the extent. So this is the, going from this one to this one uses partitions of unity, but going from the intersection to the sum uses extension. So if you have a form that is compactly supported in the intersection, then you can extend the form by 0 to U and to V. And that will be a form in this one and that one. So we have that. And then on this part, we will have H C n minus I of U. So I need a little bit more space over here. So this one is going to be H n minus I of U plus H n minus I of V. And this one is going to be H n minus I of U intersect V. And here we take compact cohomology. Now, if you look at the Mayer-Vietoris sequence, you can see that, like, you want to be able to line these up. Right? You want to line these up. But notice that when you go over to the next one, you sort of have to line up I with n minus I. The issue is when you go over to the next one, this is I, but this is not n minus I. This is n minus I plus 1. This is I minus 1, and this is n minus I. But fortunately, that's actually where, yeah, I have to put the dual symbol. Here I forgot to put the dual symbol. So this should have a dual symbol on that. So we're going to take this sequence, and we're going to dualize it. So this is just the applying the Rham functor to that sequence of vector spaces. And now it fits, and now it goes in the correct order. So we're going to have the one in the middle. This is H n minus I C of U intersect V. And I'm just going to put like a dual right over there. And then it's going to go into, so when you take the dual, you sort of reverse the arrows. So this one will go on the other side. So then we will have H n minus I C of U plus H n minus I C of V. And we take the dual. So here you have to, again, when you take the dual, that is naturally isomorphic to taking the dual of both of them individually. Small, like again, small little checks one has to do. And then that will go into H. So we're kind of going like that. We go to that one, we go to the intersection, n minus I, U intersect V, dual, like that. Then what else do we have? Then the next thing that we have is we have the one over here. This is the one, yeah, it's this one right here. We move it over. So that is going to be H n minus 1 plus, I'm sorry, n minus I plus 1. For some reason, my I looks really bad. This is, of course, I. This compact cohomology of the intersection, and it's the dual of that. And then finally, we have the last one, H n minus 1 plus I of u plus h n minus 1 plus I of v, and it's the dual of these two. And we can, so we have this sequence of vector spaces. This is an exact sequence of vector spaces because the dualizing functor is an exact functor. It preserves exactness of vector spaces. Okay, so we kind of remove this. So we have two different Mayer-Vietoris sequences. And furthermore, we have a natural map and natural linear maps that connect them together. So you have a map. This is the map that's given by integration, the map that goes from there to there. This is given by integration. So maybe I show you what that map is. Do we have it? Yeah, there it is. So these are the natural maps from the cohomology to the dual of the compact cohomology. So those are the natural maps. All of these are given by integration. It's the same exact map. It's the exact same map. And this is why it's important that these are natural maps, because they commute with the diagram. The diagram continues to commute. By the way, if you're wondering what it means to go from there to there, it means exactly what you think it means. It means this factor gets mapped by integration to that factor, and this factor gets mapped by integration to the other factor. So this is the map on the direct sum. So you have a commutative diagram. And the observation is that by the lemma that we've mentioned, the two outer linear maps are isomorphisms. So the outer ones, these two, because you see, the intersection of these two is homeomorphic to a convex open set. The same thing with U and with V and this intersection. So all of these are isomorphisms. And now you use the exactness of the sequence and the commutative diagram. So since the rows are exact and the diagram commutes, so again, the reason why the diagram commutes, that's the meaning of being a natural map. And the diagram commutes. It follows from, and we used this before, and we had it on the homework, from the 5 lemma, that the middle map, and this is the map from HI U union V to H n minus I compact cohomology of the union. Small mistake. I wrote intersection. Of course, I meant the union. I just did not write it down correctly. So this is the one given by integration, is also an isomorphism. Okay, and then you repeat, right? And now repeat the argument to show that if you have 3 open sets, that this will give you an isomorphism to the compact cohomology of the union of all 3 of them. Okay, and you repeat the argument. Basically, the way you repeat the argument, and this is going to play the role of U, and this is going to be the V. It's basically the U and V from before, but you now know that you have an isomorphism on this union, right? So it's basically the U from before, right? The U from before is going to be this new union, and we know we have an isomorphism there because we just proved it. And then the tricky part is what happens when you intersect them? Well, what happens when you intersect them and you get the triple intersection? This has to do with the fact, and this is what we're assuming. We're assuming that these open sets have been chosen in such a way that no matter how you keep on intersecting them, they will always be homeomorphic to a convex open set of Rn. And because of this, the isomorphisms are preserved on the intersections, right? And now you have just proven it for whenever you pick, this is for U, V, and W in the collection of open sets that we have in our cover, right? And continuing. If you want to make this more rigorous, you would do this as a proof by induction, where induction is based on the number of open sets you have in your cover. But there's no reason to make it rigorous. The more important part here is to understand the idea of what we're doing. That's far more important. So continuing in this manner, we obtain that we have a natural isomorphism from the ordinary cohomology to the dual of the compact cohomology. And of course, because X is compact, you can then drop the compact cohomology. It's the same thing. However, this is the part which is interesting. You need compact cohomology when you're working with the open sets, right? Because otherwise, integration might not exist if you're just integrating over an open set. So that's why you actually here you need compact cohomology. But when you finally glue everything together and you reach what you're trying to prove, then you can disregard the compact cohomology, and then you have the Poincare duality that we've presented before. And with that, we are finished. We have finished. So congratulations to everyone who followed along. Hopefully you have learned a tremendous amount of algebraic topology, and that you will find these lectures and this course valuable in your future study of mathematics, especially if you go on to learn about, let's say, differential geometry. Hopefully I'll see you again in a new course when we start.